Welcome back to class. Today's topic is controls for HVAC, and let's jump right into it. So we got a little bit of PowerPoint and some more drawings to look at, some submittals to look at, shop drawings to look at, and hopefully this is a good one. Looked at the quizzes from last week where I was asking some of the basic control stuff and realizing folks weren't doing very well on it, and I was really touching lightly on it, and probably should spend more time on this. So hence this week's lecture is going to be controls, and we're also going to do a HVAC recap, and then move on to electrical. So let's jump right in. So there's some PowerPoint going on. Okay, so the idea behind building automation and that we're using controls to process both inputs and then sending outputs to different parts of the building to be able to control the HVAC or other systems in the building and make decisions. So these controllers are making decisions based off programming and then based off of inputs. And one of the ways you can tell whether it's an input is almost always input is some sort of sensor or anyway, there's some other ways. We'll get into it. But when I was doing the last lecture and I talked about inputs and outputs, all the inputs were sensors. And I don't think anybody picked up in the quiz that you can't have an input that is motor start is a command, not an input. And so you could be measuring that the motor is rotating, but that's still a sensor. Let's move on. So the idea behind the controls, though, is that it's better than trying to manually control everything, right? So we could try and say, okay, it's hot enough in the house, let's turn off our HVAC. No, you let a thermostat do it. When the thermostat hits a certain temperature, then it automatically shuts off your furnace or shuts off your AC or whatever it might be. But if the condition that the thermostat is programmed for is not met, then the equipment is running, right? And it's just automatically trying to get to whatever set points it is. And some, like our house, has a programmable thermostat. It's nothing fancy, but at night it switches to a different set points automatically, so I don't have to think too much about it. In the morning, it turns to a different set point. Sometimes I find that frustrating because we're still up at night and it thinks or I'm up super early and it still thinks it's nighttime, and so it's not conditioning the house the same, right? But on a larger building, it has the same kinds of things where the controllers are smart, and the programming that's been done is allowing the building to function automatically and make decisions and try and optimize things. So much dependent upon the programmer who actually did that, the engineer that spec'd all those things. But a lot better, more efficient, typically, than trying to manually control it all. So some of the systems that are, I think they're kind of older, I haven't seen them very often, is pneumatic controls, where many of the sensors and things are all being done through air pressure. I'm not going to spend a lot of time on it. I just want you to know that air pressure pneumatic is what we're talking about there. It is a medium for sharing information, and at one point in time I had no idea that was a way to control system. But on a project that I worked on and for a central utility plant, they did not use any well, I shouldn't say any, but I can't think of any off the top of my head controls that weren't pneumatic in some way. And so the control systems with pneumatic definitely is a way to be able to transfer information. But more common is the DDC, or the direct digital controller, and the using electronic information to be able to both send information from sensors to the controller and also send out actions from the DDC or direct digital controller. And in this little graphic, they've got electric heating coil and electronic cooling coil. And so they're saying, hey, this little controller on the wall is getting inputs and it's then sending outputs telling this equipment what to do with this little graphic here. But that's the idea behind a controller, is that it's got a series of equipment that it's controlling. But the bigger picture you could have a simple controller like a thermostat, or you could have a whole series of controllers and it could be all tied together on a network. And this network, think of stuff that's smart, like maybe not a full laptop because that's not the way what you'd see on these controllers, but definitely that type of smarts, right? I mean, there's microprocessors. I'm not a guru, but I'm a construction guy. I don't even. But the point being, they're smart. They're smart like a smartphone. You hook up a laptop to it. You can see what it's saying. You can read all the information. You can. It knows who it is. It knows, like, it's got memory. It's got control processing power. Anyway, all kinds of stuff in these DDCs and other networks, and be able to read and communicate. So the controller over on level 1 that's running this side of the building, yes, it's speaking to the entire building automation system over its network, and it's communicating to the HVAC system on the roof, or it's communicating to whatever the system in the building is. But think of like an entire network and how diversified even a small local network in a business might be, like the printer, the computer, the storage, hard drive, anyway, all the way to more complicated business and its network. Well, kind of the same idea there, anyways, is that the building system automation, all the components are smart and they're talking to each other and they're able to do their job as they've been programmed. And you can be on a workstation and pull up on a laptop and see what's going on all these controllers, and see what both inputs and outputs are. And so there, I don't know if this is new concept to you or not, but did you know that there is a whole network inside on large buildings, and say on campus, because we've been using campuses as an example, there's a central utility plant, and I'm positive within the central utility plant there is an operator station or multiple operator stations where they can pull up what's going on in any part of any building. I'm positive. I mean, that's just the way they've been doing it for years. So, and they upgrade it and they get better and better and better, or more fancy. I don't know if better is the right word. But the point being, the building automation system, it can control as much as just a little area off of like a DDC, the direct digital controller, all the way to an entire campus, similar to Salt Lake Community College, and the whole thing is being automated and controlled. And so no one is really walking out there saying, let's turn the lights off. And we can turn the lights on and off, but it'll automatically do it if we leave and there's no motion sensor, right? So, or let's turn when there's no motion inside the room and the lights are getting turned off, let's also reduce the heating or cooling to different set points automatically. It's just automatically doing some of these things. Not that the operator couldn't force it to happen, or manually do things, but all the building automation systems taking over and making that entire thing run. Now, there's also some very large industrial buildings that I've worked on too that have tremendously complicated control systems. Just think of like what happens at the airport, or something that might happen at FedEx, or something that might happen at Amazon's warehouses here in Salt Lake area, and any of the other major warehouses that we have. They're highly automated, lots of controls. I'm not trying to get into it on this lecture at all, but I'm just trying to get to a point where you think, oh man, there is a lot. That's a huge industry, part of construction that's dealing with controls. And I'm by no means an expert in controls. I would say that if you compare it to some like speaking a language, it's almost its own language and culture and dialects and all kinds of minutia to it. And I don't know that I speak the language very well, but when I'm in the same room in meetings with folks that they're speaking the language, generally I can understand what they're talking about. But I would not say that I'm the one in the room that knows all the information about the controls. But we talked about some things that you can do to be able to understand the system, and one of them was reading the sequence of operation plan page from the drawings, and I highly recommend that. So we'll go through that again, but show you how to read some of that again. But the point being, I don't pretend to, I don't claim to know all the control stuff. It's so complicated. Um, but I do recommend, again, I've said this before in other lectures, being a student of the industry and trying to speak as many different languages as you can, whether it be the details associated with a concrete footing, foundation, rebar, all the way through to these controls or roofing or glazing or whatever it might be. Trying to be able to speak enough of those languages that you can be an effective manager and be somebody that the client would want to hire, so that they would hire you so that you can go speak all those different languages. There's no way. Um, they're not saying there's no way, but the client that's wanting their building, they have a business and they're not in construction. So why are they hiring somebody that can speak all those different languages and bring them all together and coordinate them and price them and get a contract out and deal with the city and all the other things that are associated with it, right? Okay, so talked about this before, that there's drawings, contract drawings that the engineers are going to put together on some of these more complicated or more, again, you wouldn't necessarily see it on a single family residential spec home, but on even on apartment complexes, I've seen apartment complexes with pretty good complicated building automation systems, and trying to be folks running those apartment complexes, trying to make sure that they're what control they can provide, or condos or whatever it might be, all the way to say small businesses or small spaces. They have controls in it as well. Maybe not super complicated, but definitely as you get bigger, the contract documents are going to have more and more information regarding the controls. And so because there's more and more information in the drawings, they almost always typically say, well, then I want some shop drawings or product data, or further information from the contractor to make sure that they understand the intent of the design. And we've talked about that, how shop drawings are not a contract document. They're supplemental to the contract document, that the drawings and specifications are the contract documents, and then we as the contractor or subcontractor are preparing shop drawings to show how we interpreted the contract drawings, contract documents. So definitely a whole bunch of additional information that we'll be going through. I'm going to show you some shop drawings here in a few minutes. Now, this is one of the things that I was sort of talking about in the last lecture about inputs, and it had something like analog inputs and binary inputs in the drawings. I'm hoping you're remembering that. But our inputs that the controller is sensing something. It's like telling the controller, this is what's going on in whatever the space is or whatever the system. The controller needs to know what's going on, and typically sensors are things that are doing that for the controller. Okay, so inputs are the things on the control side that are telling the controller what's going on. And then we have outputs as well, and the controller is telling actuators to open or it's closing a relay, or it's sending a signal to something else that's closing a relay. There's and then it's telling a motor to turn. So those are all outputs, and the output from the controller is saying, I sense the information, and by the logic that was given me by the programmer, or I am now asking the equipment to do this, and it's sending out information through low voltage to deliver some cooling, turn the refrigerant on. Let's regulate the airflow, right? So let's change electric heating element on. Whatever it might be, the controls are taking sensory information in, and then acting on it and telling different components what to do. And I talked about this a minute ago, but the human machine interface, the HMI, this is an old picture, but obviously this would be like a laptop. But actually, the reality is, project did just a little while ago had something like that. It wasn't a very nice looking computer. As far as the sometimes the point being, sorry, I should tell you why. Um, Sometimes they've already invested in certain software and certain programming logic or whatnot. The building has, and so it is. They want it to be consistent so that uh, anyway, maybe it does need Windows 8. I don't know, whatever, right? I mean, just saying that they've purchased some software or some control logic or language that it's speaking, the control language, and they need certain hardware in order for it to work correctly, and so they'll buy buy something that'll continue to allow that older version of it was a an addition to the building that I saw that in. They were trying to do something that was kind of like older technology, which was fine. It worked. It was working great. But you can actually see this little air handler unit right here that looks like to me on their screen, and they're looking right at, what does that look like to you, right? Well, that's a schematic. They're looking at schematics of the system, and you can see damper, motorized damper. Um, they're looking right at, and they use schematics a lot in the controls to be able to understand how the system's working, not physically what it looks like, but a schematic. And from the human machine interface, you can change the logic a lot of times from these terminals. You can force things to be on and off. On a previous project I was working on, we were having some problems, and we were a couple hours away from any major city. And so being on the job site, seeing what was going on with the equipment, we hadn't turned the building over yet. I would pull up in the HMI and log in. I knew what the password was and be communicating back to the controls contractor back in Salt Lake what I was seeing, and he'd have me force a few things on or force a few things closed, and let's see if we can get this equipment to run until he can get back out there, so we don't freeze any pipes or anything like that. We're trying to get an air handler running, and so it's pretty cool to be able to see this. And then sometimes these building automation systems, you can access them remotely from the internet, and but not the one that I was just talking about. It wasn't accessible by the internet. but some of them are, and you can access them from the internet. Somebody could log in, has an IP address and everything, and sit there and control a building from wherever in the planet you want to be, and try and figure out what's going on. Not all of them do that, but some of them do. Okay, I want to talk about signals. And the last lecture, I couldn't remember what some of the signals were, but think of just an on and off switch as one option, right? So it's either yes or it's no, or it's on or it's off, right? So power is there or power isn't there, and the sensor can be reading something like an airflow switch, right? It's either on or off or something like that, right? So or the signal to something could be either on or off. Turn the pump on, turn the pump off. And so the signals can go either way, and those are some basic signals that you could have, right? And usually this is talking about 12 volts, 24 voltage, something like that. Can think of it as like a low voltage. Definitely not like 110 or 220 or 208 or any 480, whatever it is, right? It's not that voltage, it's low voltage. And so there's another type of signal, analog signal, and it's sending signals based off of more of resistance. And so it could be saying the temperature is this, or the pump speed is this, or make the pump speed this. And so it's getting some sort of analog signal telling it more than just an on or off, more than just a yes or no. It's now able to communicate some sort of range and or communicate back to the controller some sort of range, right? So let's just do temperature. So in this one right here, the analog symbol is communicating temperature range. And so as it could be reading lower, and so the milliamps is going to be from starting here at like 10 going up to about 14, and then dipping back down to 12, and then going back to 14. And so depending on how many milliamps is being sent or being read, excuse me, I don't know if I said it right way, the controller is interpreting value based off the amperage, and so the current signal, right? And so the analog current signal. And so the programmer would say, if you're receiving this range, this means 32 at 4 milliamps. At 20 milliamps, it means 220 degrees Fahrenheit. And the programmer is telling the controller, this is what the equivalent temperatures are. And so by programming, they're translating the information, right? So then there's smarter than that, and you could have an encoded message in there. And so the whole controller could be being sent an entire message that could be very complicated, a whole series of things for the controller to do. This is not my world. I know that I know it's all done through coding. I know that it takes time on the job site to do, but just transmitted via a series of digital signals, and it's a network, and so it can communicate. And there's a whole logic and control language. There's multiple different control languages, and not all the control languages speak to each other. Some of them do, some of them don't. I don't remember which ones do and which ones don't, but the folks that are in that industry definitely do. And some communicate better over the internet than others too. I know that, but know that that's a way for information to be transferred as well on a network. So, whoops, I thought this was a good point to bring up, that what the controller sometimes is trying to do is modify the system until it hits a certain control point. And so trying to change what would be considered the offset just to make that a little bit smaller. And so it's kind of like there's this carpenter who's trying to teach me how to cut straight when I was a young man. Some people might say I'm still a young man, but he was saying if you can't cut straight on the line, try and cross the line as much as you can. And I thought that was pretty clever. And it helped me get to a point where if I was on one side of the line, of the chalk line or the string or the penciled out line on the board, I would try and cut right through the middle and find myself, no, I'm on the other side, and I'd go back and forth. But literally, I've seen that setting at the control station with the folks trying to see how this air handler is working and it modulating open and close different valves, open and close different dampers, changing the fan speed, changing uh, what cool anyway, all these parameters of the different things, and it's usually looking something like what you're seeing right here. It tries to dial it in. It's like, oh, I'm off. I've got too much of this. Okay, let's have the controller go back and no, wait, we did too much. Let's get it back, and it gets it back. Oh, we went too far, and then pretty soon it starts to like just crisscross that set point. Uh, it usually dials it in, and so the programming, if as soon as something starts up or changes modes or something like that, it's usually doing something like this where it's not right on the set point. It's trying to get to the set point, and it might cross the set point multiple times. And I think that's important for people to understand. I liked that comment because I, if it's not wrong to have it do this, this is common. And so in speaking to the client when they're looking at their HMI, if they're not familiar with it, they might think, oh, this is so far beyond. No, we just switched modes. And so we're going to see that over time, the programming is going to get to that control point pretty close, but I would expect some offsets from the actual set point while it changes modes or while the equipment starts up, right? And I think the point of this was mostly to say, hey, we could have a large variable of how much it's being controlled. And so, for instance, like humidity control, it's it's not maybe not super controlled inside of a home, like on or off. And so it might say, hey, we need some humidity and let's go ahead and turn it on. But man, it's so far from where the set point really wants it to be that it shuts off. But then it kind of gets back to a point where, oh, no, we need to turn back on. Or you could have something fine tuned like a fan speed or something like that. And it could have like a really small offset, and so really dialed in. Point being, just lots of different ways to be able to think about it. And on that idea of say humidity or something like that that might be hard to control a little bit. The parameter might be just fine to be pretty wide. That as long as it feels like people feel comfortable from 74 all the way to 70 or 70 to 74, and that feels comfortable. And so it's not a big deal if it's not right at 70. If it's not right at 72, 70 to 74 feels pretty good. And so you could expect some modulation in there that only when the sensor is reading outside of the acceptable parameters does it actually do something. So that just an idea that we could bring up. I wanted to share that as well. Now I've got this set of control drawings opened up. Hopefully Atkinson's a local controls contractor. I really like them. I hope they don't mind me looking at their stuff and using it as an example. But they've got their table of contents, and this is air handler one, wiring schematic. So we've got chill water, chilled condensing water, hot water, heating water, fan coils, VAV, um, fan filter, dual duct VAV. I'm hoping many of these things are familiar to you. Air handler, absolutely, we know what that is. Chill water, I skipped over it pretty quick, but I'm going to cover it in this one a little bit more. I'm going to kind of show you because I have a good schematic here showing exactly what they're doing. Hot water, talked about it a little bit with the boiler, but not in this commercial sense. So we're going to touch on some larger commercial um, systems here, especially since uh, building automation and what the topic is for controls. It's much more in the high-end residential homes or a commercial building for sure. So let's look at their drawings here for a second. Their shop drawings. Air handler 1 flow diagram. Something like this should look familiar to you. This is a schematic, right? We see return fan running off of VFD, variable frequency drive. So these fans are modulating, right? We got a CO2. I don't know what relative humidity. I don't know exactly what that is. Return air temperature. And forgive me, I'm not going to get all these little acronyms. I don't remember what they are off the top of my head. But this is the relief air. So relief damper. SPT-SPT. I can't come up with it off the top of my head. So I'd have to look at their language there. So we should recognize this. We know what outside air is. Outside air. I'm assuming that's an air filter, but don't know for sure. I have to read their acronyms. We got a mixed air temperature, outside air damper. So the DM, remember DM is the damper motor 2. So here's 2 dampers on this air handler, each being controlled. So think through it. Would this damper be most likely being controlled, or is it sensing information? Is it sensing information? Is it controlling the thing? So if it's being controlled, the controller is sending an output to this, right? Output is going from the controller to this to tell it what to do based off of this sensor right here. Pressure differentials, my guess is what this is, but I don't know for sure, but that's what it looks like to me. You got a pressure differential. Probably have a pressure differential here. I'm not sure. SPT, can't get it. SF supply fan. Got 3 supply fans all running off VFD. So what did we hit right here? We're now basically in the center of the air handler unit. Is this in the center of the air handler unit? I don't know. I don't know where it physically is, but the supply fans are probably by the air handler. So now we've got another temperature sensor here. I can't tell what that says. Hot water supply, hot water returns. Hot water's coming in here to the heating coil and out right back here to go get warmed back up before it comes back to here. And I'm assuming this is the valve that's a control valve, would be my guess for CV. So it's got a control valve saying, hey, open or close based off of, are we going to try and heat this air or not? So we've got a control valve being controlled. What do we have here? That's a sensor. That's an input back to the controller. ICC coil. So this is the chill water coming in here to this coil, and chill water return. No, condensing water, I'm sure. ICC. So I'm thinking that's condensing water, and that's chill water. Let's look. Okay, so what are we reading now? We're reading this information right here is in the shop drawing, but it's basically a copy of what the sequence of operation information is from the drawings. But it's described from the way the controls guy understands it. So, indirect cooling coil, ICC, indirect cooling coil. Okay, so it's got the variable air volume air handling unit. So why is it variable air volume? Because look, that supply fan is running off of VFD. The VFD is a variable frequency drive unit that controls how fast these motors are running, right? On these blowers. So it's a variable volume air handler unit. Consists of mixed air section with outdoor air, relief air, and return air dampers. Okay, got all that because we know that the return air can't just get sucked right back through the air handler and sent back out. We gotta have air exchange. We gotta change the air a little bit. We've talked about that in the past. So okay, we understand that relief air, return air dampers. Has a pre-filter, hot water heating coil. There's the hot water heating coil, indirect cooling coil right there, and chill water coil right there, and direct evaporative media. So what is evaporative media? It's like a swamp cooler. So that right there, they don't call it a coil because it kind of looks like cardboard consistency, that has water running over the top of it, and not. But the water is in Utah, because we have such low humidity. If you add humidity to the air, it feels cooler. So you can, um, and it does lower the temperature a little bit, but it actually feels cooler. So supply and return relief fans with variable frequency drive. The unit is DDC controlled using electric actuation. In the case where supply return relief fans share common plenum or duct, and isolation damper shall be placed as shown on the plans. Okay. Let's just read a little bit. The air handler unit is scheduled for automatic operation on a time of day basis for occupied and unoccupied modes. So depending on when this building is being considered open and closed, I assume that's when they have these things being occupied or not. And it's programmable. Jumping ahead a little bit, the system can enter a warm-up mode or cool-down mode. It has night heating. Okay, then it's going through. Well, what's the warm-up mode? What's the cool-down mode? What's it look like when it's occupied? The supply duct and building pressurized control. Ooh, they're trying to make sure that the building is pressurized. That's interesting. Occupied, night heating. It has some safety stuff. So the fire alarm is integrated, smoke detectors, uh, controlling the VFDs and supply fans. Well, why would that be important? Well, this is a big air handler. What I'm going to show you in a second. This is a pretty good size air handler. And this thing is running the entire building. One air handler is running like 4 floors or 3 floors. I can't remember. And so it's also in a hospital. And so if there is a fire, we don't want smoke to come back into the return air and then get pumped back out through the rest of the ductwork to another part of the building. And you definitely don't want fresh air from another part of the building being sucked into the return air, and then fresh air being supplied to where the air is where it's on fire. So we've got some safety interlocks here. Low temperature detector. We've got filter, carbon monoxide. Okay. And somebody made a comment that there are CO2 sensors located in the densely occupied spaces. So this is not anything super new. I think you've seen this on the drawings before. We've seen this kind of thing on the drawings before, but this is now the controls person's version of it. So what's new? Well, this is what's new. And so they've now shown in the various controllers and all the different control points, all the different sensors. What is that SPT? SPT, relief duct. It is a differential pressure transducer. Okay. Oh, pressure transducer is the PT, huh? I could tell that it was reading across something, so it had to be a pressure differential thing, but I didn't know what the SPT stood for. So this is all stuff that's on the air handler. And so we've got lots of different controllers. Look at this. It's saying it's going over Ethernet. Okay. Control 1, controller 2, control 3. I don't know what all these little things are. I don't pretend to. I don't speak the language well enough. But I do understand when they're talking about this stuff. I can usually get down to what they're talking about and understand it, even though I won't be able to speak the language fluently and contribute to the conversation a lot. Usually I can get there. Got the fire alarm. Anyway, so this is what they're preparing. What is this? What is this? Well, if you saw like a structural steel drawings, you have uh, the drawings from the engineer, the structural engineer, saying this is this is what the beam size is. These are your typical connections, and the structural engineer passes that into the construction documents through the permitting process. It's in our contracts now, and that's what we're building. Well, the structural steel fabricator goes and turns in, like, say you have I don't know, a couple stories like this. I wouldn't be surprised at all to see like a 300-page structural steel shop drawing showing all the different pieces, all the components, all the cuts, so that they can send that off to be fabricated and it's showing up to the site. Well, this is sort of like that. It's like saying, hey, engineer, you showed me what your control logic was in your air handler, and now we are going to detail that out in these shop drawings and show you exactly how we interpret it. And the structural engineer, I mean, excuse me, the mechanical engineer uh, can read through this stuff. For me, I see it, I understand roughly what it is, but does it matter to me whether it's points number 25, 26, or 27? No. And it might matter to somebody else, but I don't. I don't understand all that stuff. So it's okay to me not to understand. I don't need to know the level of detail that these guys have to know at, but I do need to be able to speak some of the language so that we can help. I can know who to coordinate with and help facilitate coordination, and then to be able to speak a little bit of it so that we can have it in the right contract. I can know what we're looking at when we're looking at submittals. Did they provide at least what I would expect them to provide? And so just cruising through this, we got a bunch of these, right? So this is all air handler one schematic stuff, just detailing out how the controls are going to work on air handler one. Main chiller system. Oh, hey, we've got this guy here. So the chill water system consists of one chiller with a dedicated condenser water and chill water pump. It's interesting. So here's what they're calling condenser water right there, and here's your chill water pump. Uh, or no, maybe that's not it. Maybe here's the chill water. Let's see, CHP, condensing water, chilled water. So what is this thing doing? Imagine the chill water supply, chill water return. Where is that going to? Let me see if I can split my screen enough to be able to show what this is. And this is kind of a hope on my end that we can do it. Okay. Because I do like that this is all schematic and we should be able to see what's going on. It's super important for me to be able to show this. Okay, here's the schematic of our air handler over here. Right here is our chill water supply, chill water return. Okay. Now, what the heck is that? That is coming from the chiller. So the chiller has this, it has, now go back to like uh, the heat exchanger idea. We have a coil right here. The stuff inside the coil never actually physically touches the air. All it does is transfer heat. And the heat from the air is transferred to the chilled water. And this is literally some sort of water, meaning it's water with glycol in it. This is not refrigerant. The refrigerant is inside here. And so they are saying that you have this water cooled chiller right here, and the chiller is doing all the refrigeration. It's got uh, I don't know much about the chiller on this project, but remember you have on a forced air unit, um, you have a condensing unit, a pump, excuse me, a compressor, compressor, condensing unit. I'm trying to think through all the components by myself. The thing that actually changes the pressure back. Then we're back to the evaporative coil, and then we're back to the compressor again, right? So all that is all happening inside of this, but it doesn't have. It needs help. That the condensing unit needs this chill water. I mean, this cooling tower over here that they're actually calling. What are they calling it? They're calling it condensing water, but that's a cooling tower. And so what this is it's getting water, uh, and the water is getting pumped over the top and constantly feeding in here. And then the water that gets cooled off because air is blowing across it ends up coming into the chiller and taking some of the heat out of the chiller so that it can then get back. I don't know. Condensing water supply. Where's the condensing water supply? Okay, it's right here. Sorry, I did it wrong. So that's the return. Where's the supply? Not sure how that one's actually piping. It seems like we would need condensing water. Back out here. Interesting. Because here's the supply, and it's going to come up in here somehow. But don't know. It's coming out here, over here. Condensing water is getting in here somehow, but I don't know how these are connected. I don't see it yet. Maybe there's an error. Maybe it's just me not reading it right. But I know that the water from here is getting cooled off. It's getting sent to the chiller, and the chiller is putting heat back into the water over here, and it's because it got cooled off, it can then cool through a refrigeration cycle, can cool off this water going over to this coil. Why the heck did you do all that, engineer? No, this is how it's so common. Like, this is like the larger version of what you see in front of your home. Uh, this is a really big air conditioning unit. I mean, condensing unit basically is what it is, and a condenser and evaporator in it, anyway, it's got everything right there. It just needs a way to waste its heat. So this chiller can waste its heat through this cooling tower, and when it wastes its heat, it can cool off the what's called chill water, and that chill water can go to a coil over here. All right, dude, Michael, that's super complicated. Why do they do that? And it's okay not to like fully grasp what's all going on because it's complicated. I'm sure I even understand it all. I mean, I just admitted that I couldn't figure out how the chill water supply is ending up right here. I'm thinking that these two are connected, but and there's some more piping that we're not seeing, but I'm not positive. I'm pretty sure that it's going like this, back like that. Um, but it's okay for me to not. I don't have to understand like every little part of it, but I know how it works. But I just don't know how these two are connected between these two. So but I know that there's a couple big systems. We have an air handler that's reliant upon a chiller that's reliant upon a cooling tower in order to get that coil to work. Let me say that again. This air handler is blowing air. In order for that coil right there to work, it needs the chiller, and the chiller needs the cooling tower. And in this case, they're calling it the condensing water, which is fine with me. It doesn't matter whether they just call it something different. When you look at the cooling tower, its product data, there's the cooling tower right there, and it's a big fan, and there's water just dropping right over the top of this thing. Let's see if we can find a cooling tower video real quick. How cooling towers work. Yeah, there's lots of videos. So go look up how a cooling tower works, all right? Because I don't know if I want to play everybody's video on YouTube. And I'll bet there's that dude from Engineering Explained. Whoops, shopping. Yeah, I don't mind doing that. I don't mind going. Mouse. Let's see if we can find some cooling towers and on somebody's website. eBay. Or Wikipedia. I don't mind Wikipedia being able to do. Yeah, it's something like that sitting out there. Well, the big cooling tower. See if they got a video of it. And that's probably more like what's on the building there, something like this. All right, what do you got for us, Wikipedia? Yeah, I mean, you have air blowing across water, and as the water gets down through that media, it is much colder because it has taken a bunch of the air and turned the water to vapor just by way of how much humidity is naturally in the air. And by changing some of the water from water to vapor, the rest of the water surrounding it gave up its heat in order for it to do that. So therefore, this water is colder, and it's going over to the chiller to help the chiller get some heat from the chiller. So the chiller can then take some heat from this coil. Okay. Anyway, that's probably more than you need to know. Let's keep going. Okay, we were talking this one right here. We're back on controls, and I'm just trying to explain. We have a large building, a whole bunch of shop drawings are being made. And so what would you expect after this? Because this is the drawing, this is the schematic for the chill water system. That is the sequence of operation for the chill water system. And what would you expect following that? Controller information. All the controllers and the wiring, more controllers, more wiring. Oh, now we're on to boilers. Boiler and hot water. Let's follow this. Check this out. Hot water return, hot water supply. Where does that go to? Here is the air handler, and it has a hot water coil. Hot water supply, hot water return. It's coming from these two boilers. One of these two boilers or both. I'm not sure. We'd have to read the sequence of operations, see if they're both operational or one's a backup. It doesn't matter. I'm hoping you just saw, what do we have here? We have some hot water pumps run by VFDs. What's that? That's a sensor. What's that doing? That's being sent back to the controller. That information is being sent back to the controller. How effective was our hot water? Hey, are we doing okay? Anyway, got a valve right here, a check valve, probably a motorized one. Why? Because they're deciding whether to let this water go in here or not and get warmed. I'm sure there's a ton of controls for this as well that we're not looking at. And so what would you expect following this? I'm hoping you're saying we're going to get more control drawings. Yes, we are. We're going to get a bunch of control drawings with a bunch of points. Yep, whole bunch. All right. Lots of information. All right. Trying to decide. Let me stay on what you'd see in these shop drawings, and then we'll tell you why it matters. All right. Remember how we said we have a network? Let's get back out of this. Oh, come on. I was saying that the controller can run off of a network. So just trust me for a second. Well, you don't have to trust me. I'll just show you. All right, this little symbol, that's a VAV. What's VAV? Variable air volume. They're inside of a duct. They're in the ceiling space. That's a little thermostat wire. backnet and power, and a transformer, Phoenix router, network tag, ID tag. All right, we got the legend, but just check it out. You have a thermostat, it's connecting to that VAV and that VAV. This VAV and this VAV are connected via one orange and one red. What was orange and one was red? The backnet versus the power. There's the network, there's the power. Network power, network power, network power. Now, this EOL, end of line, I forgot, network. So this is the end of the line for the network. And it must be going somewhere after this. So is it an exam room? So this is going, this is must be feeding somewhere information to some other part of the building right here. But that would be like, that's the heart or the brains of it all. And we've got the whole thing all connected up. It's all one network. Should this, wherever this end of line goes to next, the network right here, wherever it is, uh, it can read and sense basically and control everything because it's all connected. It's one big network. Do these lines mean that that's physically where the wire is? No, absolutely not. This is in conduit in this building. I'm sure it's running kind of like perpendicular or square. I would really doubt that there's free hanging wire sitting in the space right here. It might be in cable tray, maybe. I'm probably wrong there. It's got to be in conduit. Anyway, it's in some sort of raceway. So, but look, it's all connected. It's all connected. All right, cool. Let's look at the next floor. We got more ductwork. This is all existing. This is what they want to add in. All right, cool. Got more. Here's the next floor up. Do you have to be able to read all that to understand it? No, it's just realize everything's connected. And to the controls contractor, this is what they're going to be doing. They're going to be running all this wire. They're going to be running all the thermostat stuff. And so now comes the time where I'm talking about being a general contractor. Now you're on this type of a project right here. I tell you what, the controls contractor is, and the control wiring is something that needs to land in somebody's contract. Is the low voltage wiring being covered by the person installing the VAV? Well, the person installing the VAV is mechanical contractor. Do they have a low voltage company or a low voltage side of their company? They're going to hire it out. Do I need to, if I'm going to hire this mechanical contractor to be able to do this, do I need to, as the general contractor, go hire another control contractor to be able to do all this control wiring for them? Because typically the people doing mechanical duct do not do mechanical wiring or low voltage wiring. Who's going to do the controls for it all? Well, if I was a project like this, I'd probably make it all turnkey with the mechanical contractor. Mechanical contractor, you're going to provide all the ductwork, you're going to provide in your contract, you're going to do all the low voltage wiring, you're going to be responsible for all the controls. But that might not be the most cost effective way to do it. And so we could send that out to bid to different ways and say, okay, well, maybe our electrical contractor thinks he can do all the low voltage wiring, and we just need to hire a separate controls contractor to do that. Now, it can be done lots of different ways. My point is there is a lot of work to be done. And so from a contract standpoint, you already saw the submittal standpoint. Now, from a scheduling standpoint, there's a lot of work to be done. And notice that kind of like everything is sort of like connected, right? And so how much programming time is there that the controls contractor needs after the wire is pulled, after power is on, after things are started to do programming? It's a big deal. So at the end of the job, when can you actually have lighting and power to all this stuff? When can you actually run it? Well, it has to be pretty dust free. So the controls contractor is going to be in here doing some work. How much work can you do before uh, how much programming can do before we turn all this stuff on? Well, probably got a bunch of time there too. And so, kind of the point being, don't ignore the controls when we're scheduling this stuff. And its work is just as valid, if not more valid, as like something that you see, like flooring go down or paint go on the walls or the lights get turned on. The controls can be complicated. It can be a lot of work to be able to put all the controls in and program it all. Now, there's some tricks associated with the language, I think, and being able to understand how much. One of the things that I think is important is knowing where the main controllers are and what the main controller is controlling. So if this floor only had like one controller, which I'm not positive, I see if we can find it. Forget it. The point is, if you know where it's like an electrical panel, if you know what the electrical panel is feeding, when the electrical panel is all tied up, I mean, it's all terminated and wires are all done, and assuming the panels that are feeding it are all terminated and clear for power, we could turn those on. So knowing where the main parts are that are controlling everything matters. And then now let's talk about floor to floor to floor. What you don't know, and I should show you, this is the roof, and this is the air handler, and here is the chiller, and we've got chill water pumps over here, and the cooling condensing water cooling tower right there. So all this stuff is on the roof: air handler, chiller. Where are the boilers at? Okay, boilers are over here. We talked about boilers. Um, Here's probably the boilers, pumps. All this stuff is on the roof. Now, say we're doing a typical construction and we're trying to work bottom to top. This doesn't mean as soon as you have the ductwork and the wiring done and power on here, it does not mean that this works. It's operational. It doesn't mean that it's functional. You might have multiple floors to be done before we're to a point where we say, okay, we can function as a system, or maybe you can. But the point is, you got to get with the understand the system well. And it just I've seen that. Let me share a story. So I've had this sitting in a meeting where the project manager was saying, when are we going to start that chiller? And what he wanted to do, what the project manager wanted to do on this large project was cool the building with the air handler. But instead of asking about when am I going to be able to cool the building with the air handler, he kept saying, when are you going to start the chiller? When are you going to start the chiller? Well, the chiller is one component in this entire air handler. It has nothing to do, I mean, it doesn't, just because this thing is running doesn't mean the air handler is running. It doesn't mean that all this other control stuff is running. It's the wrong question to be asking. It's the wrong question to be planning. So I think it's a good thing if you're asking as a general contractor to follow up on components. Tell me about the status of the chiller. How much more work do you have before it is operational? Uh, what status are we with the startup or that kind of stuff? Or the same thing with the boiler. Have we flush filled and tested the boiler piping yet? Is the boiler operational? It doesn't mean that the boiler can do anything yet. So have we started the air handler to a point and given a demand to the boiler that the boiler can now operate and be tuned and running and provide consistent heat to the building, consistent heat to the air handler. That not when is the boiler going to get started or when is the chiller going to get started? Uh, Literally, what starting means is somebody turned this motor on and it started the boiler pump, or they provided power to this boiler. It does not mean that the rest of the building can be using what is being what heat is this boiler is generating, because the heat's going from here to this air handler through all this ductwork all the way to these things, which are then controlling it, right? I hope you're seeing that. I'm hoping you're seeing that it's a pretty dang complicated system. And when I first brought up that lecture saying like, what do you need on your sink, your kitchen sink? You go to your kitchen sink, and what do you need your kitchen? What systems do you need for your kitchen sink to work? Well, we need water. Okay, that's good. We need sewer because we need the water after you use the kitchen sink to go somewhere. But we've also got uh, what else do we have there? We have what? How does the water get hot? Well, then we need natural gas. We need water service. We need water meter. Okay, we're to the edge of the house. That's water taken care of. What about electricity? Do we need electricity at the um, kitchen sink? Yes. So my point of the whole thing of doing that what does the kitchen sink schematic need was for you to realize that even a kitchen sink is fairly complicated. You might look at this and go, no doubt this is complicated. Obviously, this is complicated. And yes, it can be very complicated, but it's not so complicated that it can't be sequenced. And someone like myself who doesn't speak the entire language, if I know not to talk about specific components, but talk about what my outcomes are, I want to be able to heat the building with the air handler by this date. What do we need to do that? Uh, Mr. Mechanical Contractor. If I know enough about it to be able to make sure that I have the right interface between controls, power, and equipment. So all the VAVs, uh, each one of them has control, power, and it's a piece of equipment. Do I have all my contracts sort of like dialed? I don't need to speak every single line, every single part of the language to know I can get that all coordinated by understanding some basics. And this class isn't there to teach you like every single piece of minutia to be able to write a contract. All I'm trying to do is give you some foundational pieces and understand. Hey, this is what you're going to see in a large commercial project. Okay, so we looked at the control. Let's finish off this submittal here. We've got what is this? This is the points list, parts list, part number. All right, well that's great. Valve schedule. There's a bunch of valves. We've shown these before. There's the Belimo actuator on a ductwork. You guys have seen that before. Yeah, for sure. I talked about that in another lecture. You've seen these pictures right here where, oh yeah, that's a damper and that's a motor on a damper. Okay, cool. So what do we got here? We got us a little actuator right here. What does that totally look like? That looks like a VAV box. More control stuff. Got how to assemble it. Not sure that I need to know all that, how to assemble it from my point of view. I'm glad that it's in there because this information is good for them to have. We've got some butterfly valves, Belimo butterfly valves. Look at that. So there would be an actuator on top of this, opening and closing this valve. Not actuator not shown. Hey, there we go. There's a good picture of it. So they're planning some of this stuff where the valves are being controlled by an actuator, right? So there's an output from the controller saying, open this thing. Guess what? They're interlocked. Like one can't, it looks like, I don't know why, um, but for some reason they are. Hey, little guys, some little Belimo, uh, little valves controlled by Belimo motors. All right. Oh, right on. What do we got here? Zone valves? No idea. Now, as I was planning this, oh, here, now we got to some equipment finally. The Jace 8000 controller by Siemens. Sweet. Love that piece of equipment. Actually, I have no idea. We've got a Delta application controller. It's a fully programmable native BACnet. BACnet's like some sort of control language. I know that it means that it can go to like building automation, but I don't know a lot about BACnet. And I might not be exactly right on exactly what that is. Like, I know that it's control logic or language or something like that, but or it's BACnet compatible or something like that. It doesn't matter to me from my point of view. I know that when we're dealing with that kind of stuff, the BACnet, all this, it's part of a larger building automation system, and so they need to be speaking together. If this is a part of a campus or this part of like a larger, again, this was part of a hospital, so it matters a lot that the facility people that manage the buildings, they do not want things that are not compatible with their existing systems. So I need to facilitate coordination between the mechanical contractor, the controls, and also the folks that are on the owner side that will be able to take care of this stuff. And those are things that I need to start doing early on. Get those people to be able to have each other's phone numbers so they can communicate, as well as they needed to go through anytime there's a design change, go through the designers, or there's a fundamental change, but typically just need them to communicate a little bit. Okay, so you're seeing, oh man, what is this? What's an IntelliBus control system component? I don't know, part of the controls. We got a board here. So this is really just going to my previous point. There's a lot of work to be done on this building with regard to controls. So contracts, submittals, scheduling, and guess what? We haven't talked about it yet, but commissioning. There's going to be a lot of commissioning, making sure all this works. Got transducer. So pressure stuff. Okay, well, don't think that this is the end of the day if you're not following what this is. All I'm showing, again, is there's a lot of stuff regarding controls that we need to be paying attention to a little bit. We need to help facilitate and coordinate. And like from a general contractor standpoint, I came from the steel side, from civil, from exterior envelope, and then got into the general side. And I spoke a bunch of those languages already, but the languages that I did not speak were mechanical, electrical, controls, and I've had to learn it. And so being a student of the industry, man, looking things up, making sure at least I understand, paying attention, don't just like, I'm never going to understand it. No, this is completely understandable stuff. You have to be exposed to it. You have to have somebody that can help you a little bit, but totally just don't ignore it. Dive in, try and understand as much as you can. And in the modern day of Google, man, you can get to pretty quick what's going on. All right, now I want to talk a little bit more about some sequence stuff. So when we looked at, here's some more control stuff. We got VFDs. This is the whole network right here. Talking about that. Let's see if there's anything in this thing I want to cover. Yeah, I was just going to show more parts and pieces. I'll just close that. So let's go to this. Okay, this is the big air handler that's on the roof. And from a plan view, meaning from the top section, we've got the evaporative cooling section. We've got motors for the blower. We've got coils right here. Looks like RF VFDs. So is that relief or that's supply, that's return fans? They are in the same unit. Interesting. Okay, let me go find that big diagram. Right there. Okay, this is the roof of a building. And now, what did we talk about with relative to this piece of equipment? This thing is so big that it is going to have to be either lifted and sectioned or built on site. And what it's on the roof, so it's got this little structure going all around it, little penthouse thing. And so as you think through, this is pretty complicated work. And so this is, some folks will just be like mechanical on the roof. No, this kind of thing, this kind of space with all this tight stuff would be a great candidate for using BIM or virtual design, VDC, virtual design construction. So VDC or BIM, like the BIM model type work. And I believe this building actually got that. But there is a lot of coordination among piping, among how to locate all these the pumps, how to get all. Anyway, this is a busy space. Great candidate. Also, a great candidate to spend some detailed planning on how to build this thing, how to do logistically to get things up here. How are you going to get big boilers up on the roof? How are you going to get this chiller up on the roof? Is that all crane? Well, how does that sequence with this penthouse? Do we have to get the penthouse roof built after the chiller? Do we leave out a section of the roof? Are these being brought in as sections? All early planning stuff that needs to be discussed as probably even through estimating a little bit all the way back into there, how we plan to do a little bit of this penthouse on the roof. At least put together a decent plan and understand what the mechanical contractor that we're going to hire is going, what their plan is. Maybe this is all crane and maybe it is all fabrication offsite and it's going to come in sections. And so definitely you're going to have to leave a roof off for a long time. If you're going to leave the roof off for a long time, how are you going to get to the finishes down below? Oh, yeah, that's a problem, right? Okay, we might have to sequence this. We got to get this watertight because this is up on the roof. We can't do any finishes. We can't drywall, do any insulation or anything until we have this watertight. So I was on a project, one of my first, and the owner sort of dictated what side of the hotel we started on. And we started on the side without the air handler. And had we done that again, we started the side on the side because the owner was doing the earthwork. It wasn't in our contract to do the earthwork. And they built the pad for the side of the hotel that did not have the air handler in it first. Well, when it came time, and it was the Kimball Junction Park City area, came time to heat the building, we were running a lot of temporary heat because we did not have the side of the building built early that had all the air handling, mechanical equipment, and that kind of stuff. It can be a real challenge to think like that mechanical, electrical, those types of rooms are super important to pay attention to and schedule and get sequenced in first, as well as the submittals. I think submittals are kind of like easy to understand that now this is long lead equipment, got to get it through the submittal process. But you have a lot of work that gets coordinated, and there's a lot of specialty type things in here that need coordination. Hence BIM or VDC. Hence getting contracts really dialed. There's a lot of things to pay attention to right here, and it can be really fun and really challenging. In fact, something that I really enjoy working on is this type of stuff, all the way through to the end of the project. A lot of really good stuff. All right, I wanted to do an overview going backwards to try and wrap up HVAC. So let's do that. We started this whole series off talking about comfort, temperature, and we were saying like the residential versus the commercial side. What did I just talk about? I just talked about like larger rooftop units, chillers that kind of look like this. We just got to some of these right here. But the the early things that we were talking about matter, ventilation, temperature, humidification, dehumidification, filtration, circulation, right? And all of those things, it doesn't matter whether it's uh, a large commercial project. Those same kinds of principles matter, and that's what we're talking about for HVAC, right? Those were the principles that mattered. So we had kind of this residential, very simple uh, with the cooling section. You guys can see that now. Heating section. What's that look like? Looks like clamshell. I don't know. Or the air conditioning condensing unit on the outside versus a large boiler, steam boiler, or a chiller. And we talked a little bit about humidification and what that does. So going all the way to this idea of we need to circulate the air and make sure that the air is getting enough air exchange. We talked about outside air, inside air, combustion air. Uh, we got into the return air. So we got outside air, return air, we combustion air, supply air. Uh, got to a whole bunch of these different types of air, right? Exhaust air, right? Exhausted air. Then we talked a lot about the heat exchanger and brought up this idea of transferring heat to the conditioned air. And then the heat exchanger idea, I've been trying to build on that for a long time. This is the furnace and the heat exchanger in the furnace. And the heat exchanger in the furnace is easy because it's heating. But the idea behind heat exchanger doesn't always mean hot, mean relatively to us. It just means we're transferring heat. So it can be a little bit of a hard time to think heat exchanger. Maybe I should start by saying heat exchanger is not transferring heat. That's hot, transferring heat that's we think is cold. But the point is, I was trying to describe a heat exchanger. And by the end of this whole section, I think you've seen how cooling tower to chiller to coil inside the air handler, that's all heat exchange. It's just moving heat from one spot to the other uh, and trying to get heat outside of the building. So we talked about how this is the blower section. We've got the air going up through this space right here, out this duct right here to the house. The combusted gases being inside here, coming out the flue. The combusted gases heating up this metal of this heat exchanger, and the air that's passing over it from this blower getting hot, right? Talked a lot about that. And then we got into refrigeration. Let's see, we got one right there. We talked about how there's a cooling section of your furnace, and it's called the evaporator. And we've got the condenser compressor unit outside, made up of a compressor and a condenser, and the refrigerant going back and forth between the two. We talked a little bit about how there's controls and other things associated with that, and thermostats, and we got into a little bit of controls here. And now you can see, I'm hoping that on the much larger project, it's the same basic principles. It's the thermostat. It's trying to control multiple pieces of equipment and just how smart it is, how much equipment is involved. Same kind of thing. It's really just something simple like turn the fan on. Will you make this coil work? Will you work on the refrigeration? Will you open and close this damper? Hey, the thermostat says that it's fine. The pressure switch, it's not very complicated if you think about it like from this perspective. Just little pieces you've gotten, and you should be able to apply them to the larger pieces. And we told you like there's controls inside your HVAC system in your home, differential pressure switch, high pressure switch, all kinds of stuff. Well, all that stuff is also in the larger projects. We went through the mechanical refrigeration process, right? Where the gases is compressed, starts to condense into a liquid. As it turns into a liquid, it's releasing some of its heat by a fan, blowing air across it. We're getting the liquid back to the expansion device. Liquid is changing back to a vapor. It needs heat in order to change to a vapor, so it pulls the heat out of this air that is a fan and getting back to the compressor. That is what a chiller is doing as well, but it's not using air to cool. It's using water to cool it from the cooling tower. Or sorry, this side over here, the the condensing side. Instead of using air to cool it, the air it's using condensing water. What's cooling the condensing water? Air. Why? Uh, no idea all the engineering. I just know that it's a larger scale and it works. Then we got into HVAC zones and VAVs and FCUs and economizers, just some larger pieces of equipment, right? We talked about zoning and how this one air handler unit, it's got heating and cooling, but there's only one thermostat, and the heating in this side in this room is gonna be require more heat, more cooling, because this has got sun coming right through the window. So this office is going to need more cooling, and that's where the thermostat is. But this room is getting the same amount of cooling as this room, and there's no heat, or there's less heat gain in this room. So this room is literally going to be colder, because it's getting the same amount of cooling requirement here, or it's calling for the same amount of cooling requirement here, where there's no sun to heat up this office. And then we talked about how, well, let's control each of them with a VAV, variable air volume, right? Well, what does the VAV do? It's this box, VAV box. It has a little damper on it, opens and closes, allows more or less air to come in. Then we talked about how there was a reheat coil on that as well. A VAV with a reheat coil. And they could actually do more than just regulate how much air. They can actually heat the air back up. And that seemed crazy to everybody, right? So why would they do that? But that's how they do it. And so now we're back to the more complicated stuff, that this really isn't that complicated. You could be much more complicated. But for the purposes of this class, if you got all the way to here and you're kind of like grasping what's going on, that's really good. That's fantastic, and I'm super pleased that you got that far with me on HVAC. There, it can go super deep. We never really covered like a bunch of more. Anyway, there's a bunch of equipment we could have gotten into, a bunch more systems we could have gotten into. We didn't. That's okay. If you got here and you're following to this point, uh, I'm hoping that really helped you in your career. So we're going to move on to electrical from here, and should have a good time. But thanks for taking this trip with me through HVAC. And next time we talk, we'll be talking about something different.